Hi, in the last session, we talked about shift registers and we also designed it in VHDL. We have also developed a module for serial in parallel out system using this shift registers. Now let's talk about serializers in VHDL and let's see how they works and how to design a serializer in VHDL. So let's start. So first understand that what is serializer. In simple words, serializer takes the parallel bits as an input and convert it into single bit output. Means it is a parallel in serial out system. So it takes parallel data streams and send the data to the output. Of course, in a sequential manner. Now question is what it do and where they are used. So these systems are widely used in digital systems and communication systems, etc. Why? Let's understand this with one simple requirement. So you have 32 bits to transfer. So if you have 32 separate lines, then you can simply transfer each bit on every line. And you can transfer all of your bits in just one clock cycle, right? But if you have just one single line where you need to send this 32-bit data, then how you will transfer it? Simple, because we assume that one line can carry one bit at a time. So you need to send one bit at every clock cycle, right? So here serializers can help you. How? Well, it will break down your 32-bit data into one single bit and pass that single bit to the output at each clock cycle. So the benefit is that you do not need to set up 32-bit channels. You manage to do it on one single channel. Of course, it takes 32 clock cycles, means more time to transfer same data compared to the parallel transmission. But still, you have a choice that how you want to do it. So at the transmission side, you use serializers, which will help you to send parallel data over a single channel. Then you will need a reverse system of it, which can take the single bit stream and convert it back to the original data stream, right? So we talked about that serial in parallel out system in the last session. So serializers are just reverse of that serial in parallel out system. If you have not seen that video, then please refer that after this one. Now coming back to the implementation part of serializer. So we need registers or flip-flops to implement a serializer. So in VHDL, we will use registered process block. So it will capture the parallel input data and shift that data one by one at every clock cycle. Means it will be synchronized with clock signal. Now in our example, we will use generic to design our serializer. Why? Because by using generic in VHDL, you can adjust its parameter for different application needs, such as width of your parallel data input. For example, you need it for a 4-bit parallel inputs, or for some other projects, you need 32 bits parallel input. So in such cases, you do not need to change your whole VHDL code. You just configure your generic parameter and boom, your whole design will work according to that. So that's the power of a configurable design, which you should practice always. So let's start with the implementation. This is the block diagram of a serializer module, and we will be designing this module. Let's quickly understand it. First, focus on input ports. So we have reset and clock signal. Reset is needed to initiate your module, and clock signal is needed for the synchronized shift of your data. Next, we have input D in. So this input is STD logic vector signal and have parallel data streams, which we will be converting into the serial data stream. Now I have mentioned N with this port. So this port has N number of bits, and we will be using generic to define this N number in our VHDL code. Next, we have shift enable input. Means when this port is enabled, then only your data will start shifting. So it is an additional control. At the last, we have load input signal. This is important because when this pulse is given, your serializer will capture the parallel input data. Note that when there are multiple bits connected to your hardware, then they are always connected. It's not like you connect one pin at a time, then connect another, then connect another. It's not happening, right? So when all these inputs are always connected, you need to tell your module that specifically when it had to capture input data. And once it is captured, it will start moving that data to the output one by one. Note that it is just kind of a pulse, means you give it, then serializer will load that data and start transferring it. If you continuously triggered it, then only one single bit will be transferred at the output and that have no use. So, in short, this input signal indicates that when exactly it has to capture new data from D input into the serializer so that it can ensure that the right data is loaded at the correct time. In the last, this module has one single output, that is D out. So it is single bit output. So let's code this in the next slide. So this section is library declaration and entity declaration of our module. As I said, we will be using generic for flexible length of our input signal. So this is our library declaration first, and it is library IEEE use IEEE.stdlogic1164.all semicolon. Next, we have entity declaration section, and it is entity serializer is generic width colon integer bracket closed semicolon put clock in std logic reset in std logic shift enable in std logic load in std logic in std logic vector width -1 down to 0 dout colon out std logic bracket closed semicolon and entity semicolon. Because this is very straightforward and we have explained it many times in previous videos. So I'm not explaining it again here. But in short, we have defined a generic parameter first, which is named as width, and then we defined all the input output ports of our module, which we have seen in the last slide. So we have input ports, clock, reset, shift enable, load, and D in. We have one output, D out. Just remember that D in is std logic vector and its range is flexible now because it is width -1 down to 0. So if width is 4, it will become 3 down to 0. And if width is 16, then it will become 15 down to 0. So next is architecture section. So this is the architecture design of our serializer module. We start the architecture declaration. So let me read it first and then we will explain it line by line. So it is architecture behave of serializer is signal data register colon std logic vector width -1 down to 0 semicolon begin serializer process colon process reset comma clock begin if reset equals to 1 then data register gets the value of others are 0 semicolon else if at rising edge of clock then if load equals to 1 then data register gets the value of D in. Else if shift enable is equals to 1 then data register gets the value of 0 concatenated with data register width -1 down to 1 and if and process then D out gets the value of data register 0 and architecture. So architecture name is behave and module is serializer. Next, we define the internal signal and this is data register. This is std logic vector and having the same range as input D in. So what it will do? Well, it will hold your parallel data when you load it. Remember, I explained this in the block diagram. And then this data will start transferring to the output at each clock cycle. Next, start your architecture with begin keyword. Next, we start a registered process. So, sensitivity list includes clock and reset signal. So, first is reset condition. And when this reset is asserted, your internal signal, which is data register, will reset to 0. So, the statement I have used is data register gets the value of others are 0 semicolon. I already explained this statement many times before, that how it moves 0 to all the elements of vector signal despite of its length. So you must know that why we have used it here, because we used generic to adjust the width of input signal. So we don't know that it is 4-bit or 16-bit or 32-bit data. So we cannot hardcode a fixed length value here. So when reset is asserted, then this data register is cleared. And after reset, you are ready to capture your input data. Next step is when load is enabled or load pulse is given, then we want to load our input DIN data into the internal signal, which is data register. And we want to do it in the synchronization with the clock signal. So we check for the rising edge of a clock signal first and then used that condition. If load is equals to 1, then data register gets the value of D in. Means if load signal is asserted, then we will capture parallel data from D in and we will store it in our data register. Next, we used else if condition. That else if shift enable is equals to 1, then means when this shift enable input is enabled, then only our shifting will work and your parallel data will pass to the output one by one. Now suppose shift enable pin is active, so we need to write our shifting operation. So we have written this statement here. Data register gets the value of 0 concatenation with data register width minus 1 down to 1 semicolon. Note that this statement will trigger at every rising edge of your clock signal. Means at every rising edge, 0 will be asserted at the most significant bit or MSB, and it will be concatenated with data registered width minus 1 down to 1. So 1 bit will be shifted out from data register at every clock cycle. This is what this statement will do. So this statement is the key statement of this module. And this statement is actually doing your shifting operation. So let's understand this once again. So we inserted 0 from the left side of the data register using the concatenation operator. Why? Because 1 bit is shifted out from the data register. As the new range is data register width minus 1 down to 1. And now data register length is not matched. So this is not allowed in VHDL. Means we need to add one additional bit to the register after shifting 1 bit from it. So your LSB or least significant bit will be transferred first. This is a common requirement in many serial communication protocols. So this complete your requirement of shifting. But till now, we have not assigned any data to the final output. But before assigning it, let's terminate all the if conditions. Now you can assign LSB or least significant bit of your data register to your final output. And you can do it inside the process block at the end of all the conditions so that your data gets transferred at the output. Remember, we have explained how this assignment works inside the process block. Inside the process, the last assignment on the signal takes place. So you can write it just before terminating your process block. Or you can assign it after terminating your process block as well. Means inside your architecture body. If you do so, both of your statements will execute concurrently. I mean your whole process block and this output assignment. Now you might confused that we hard-coded data register 0 bit to the output D out. Then how it will shift data and how I will get all the input bits one by one at the output, right? Well, that's true that we have hard-coded bit 0 to be transferred at the output. But this bit 0 of data register getting shifted by 1 bit at every clock cycle. So at each clock cycle, this bit will be overwritten by the following bit of your parallel data input. So this is how it works. Finally, terminate your architecture section using AND architecture statement. So this is our VHDL code for serializers or parallel in serial out system. Okay, so that's it for today. In the next session, we will design memory elements such as RAM or ROM, etc. in VHDL. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.